Good morning. What you'll be seeing over that. So the next unit is about a finite word length effect. Okay. So the topics what we have to see over on it now: fixed point and floating point number representation, ADZ, quantization noise, and then what about input or output quantization, coefficient quantization error, product quantization error, overflow error, limit cycle oscillations due to product quantization and summation, and what about the scaling to prevent overflow. Okay, so when we are designing a FAR filters, so we know that the filter coefficients are determined by system transfer function. These filter coefficients are quantized or truncated while implementing DSP system because of finite length registers. Only finite number of bits are used to perform the arithmetic operations. So typical word length is given over here to be 16 bits, 24 bits, and 32 bits, etc. Okay, the finite word length which introduces an error which can affect the performance of the DSP system. So we have a three major errors. The three major errors are to be input quantization error, coefficient quantization error, and the overflow and the round off error. Okay. So this effect of error, which is introduced by signal process, which depends upon the number of factors, which includes the type of arithmetic, quality of input signal, and type of algorithm implemented. Okay. So when you are saying about an input quantization, coefficient quantization, product quantization, so the conversion of continuous time input signal into digital value, which produces an error, which is to be named as an input quantization error, where these error arises due to the representation of the input signal by a fixed number of digits in A to D conversion process. Whereas in the case of an coefficient quantization error, the filter coefficients are compared to infinite precision. If they are quantized, the frequency response of the resulting filter may differ from the desired frequency response. That is, the poles of the desired filter may change, leading to instability. And the last one to be the product quantization error. It arises at the output of the multiplier. When a bit data is multiplied with another B bit coefficient, the product should be stored in B bits registers. The multiplier output must be rounded or truncated to B bits. This is known as overflow and the round off errors. So these are the three different types of errors which is introduced by a signal process, which depends upon the number of factors, including the type of arithmetic, quality of input signal, and type of algorithm implemented. Okay. So now let me see the next to be the what are the types of number representation. So we'll have a fixed point representation and floating point representation. So let me see, explain the various formulas of fixed point number representation. In a fixed point arithmetic, what we can know that the binary of the, that is the position of the binary to be fixed one, the bit to the right, which represents the fractional part of the number, and the left represents the integer part. So for example, if you are considering the binary number 1.1100, which will be getting the value 1.75. So what we should do it of, the position of binary point is fixed, which is given as an 0 into 2 power 1, 1 into 2 power 0. That is the left to be the fractional part. And the next one, this will be multiplied with the 2 power minus 1. This will be the integer part. 1 into 2 power minus 1 plus 1 into 2 power minus 2 plus 0 into 2 power minus 3. So finally, we can able to get the value around 1.75. Okay. So in generally, we can represent the fixed number n to any desired accuracy by the series. So n can be equivalent to summation I is equivalent to NTCI Ri, where Ri is called as an radix. If R is the 10, the representation is known as the decimal representations, having the value from 0 to 9. So in this representation, so we can able to get that 3 into 10 power 1 plus 0 into 10 to the power of 1 0 and 2 to the 10 to the power of minus 1, 8 into 10 to the power of minus 2 plus 0.5 into 10 to the power of 3. So if R is equivalent to 2, so we have to replace the radix value based on the radix value. Okay, if it is 2, we know that this is a binary representation. If it is 10, it will be represented as a decimal representation. Okay. Let me see the recollect. Already we know that how to convert a decimal into a binary form. We'll be using of a division method. So if you are having of an integer part 30, so we'll be dividing with the help of an 2, so that we can able to get from 15, the remainder will be 0. In dividing 15 again with the help of 2, we get the remainder value to be 7. The remainder will be equivalent to 1. And again, when you are dividing 7, the value will be equivalent to 3, 6, and 1. Remainder will be equivalent to 1. And finally, when you are dividing the value of 3 by 2, the value will be equivalent to 1 with respect to 1. So we have to write from the bottom to the top. So we get a value 1, 1, 1, 1, 0. And for the case of 0.275, so we have to multiply it with the two value, which is equivalent to 0.55. that is with the representation of 0 to be the next one. 0.55 will multiply with the value of 2. 1.10, we have to take out 1 to be the out, and 0.10 into 2 will be having on 0.20. 0.20 will multiply with the 2. 0.40. 0.40 into 2. 0.80. 80 into 2. 1.60. 0.60 into 2 is equal to 1.20, and 0.20 into 2 is equal to 0.40. So we'll be writing from the uh, top to bottom. So 0, 1, 0, 0, 1, 1, 0. So decimal is converted into 1, 2. So in a fixed point arithmetic, the negative numbers are represented by three forms. So we'll have a three different forms: sign magnitude form, one's complement form, two's complement form. So when you are representing sign magnitude form, so here an additional bit which is called as an MSB. So if this bit is 0, which represents positive number, if the bit is 1, it represents a negative number. Okay. So 1.75, so which is represented as an 0, 1.1100, minus 1.75 will be represented as an 1, 1. Okay. So 0 now, which represents positive, 1 now, it should be negative. So one's complement, we know that the positive number is represented same as that in sign magnitude form, but the negative number will be obtained by complementing all the bits of the positive number. For example, minus 0.875, so it will be represented as an 0.11100. In the case of minus 0.875, we have to take the complementing. What's the meaning of complementing? That is that we have to convert zeros into ones and ones and zeros. So it will be replaced as an 1.0001111. Okay, that is the complementing of each bit. The next one to be the two's complement. So two's complement is to be that we have to take a one's complement and we have to add with the one with the one's complemented value. So for example, 0.875, when you're taking one's complement, 1.00011, we have to add with the value of 1. So finally, we'll be getting the value of 1.001 into 000. So this is the way to use of your sign representation in terms of sign magnitude, one's complement and two's complement. So let me see some examples. So which is converted into minus 7 by 3. So 7 by 3, that is to be a 0.21875. So when you multiply by 2, so we'll be getting of an 0.43750. Then again to multiply by 2, 8750. 8750 multiplied with 1.75. 0.75 into 1.5. 0.5 into 2 is equivalent to 1. So the representations can be given as an 1.00112. So what is the one's complement? So we'll be getting, we have to take the zeros, we have to take the complement value, zeros and ones. So 0 will be replaced as 1 when, and triple will be replaced as an 000. I have to add 1 with the value of an, you have to add 1 with the value of an one's complement value. So which is make that the final value to be 1.11001. So in the case of an minus 7 by 8, so what will be getting? So 0.0111. One's complement will be 1.000. And finally, we'll be getting of an 1.001. So plus 7 by 8, we'll be getting the same value as 0 of a sign magnitude. The next thing we are going to see about, and what about the addition of two fixed point numbers. So let me add the value of 0.5 and 0.4. So the value to be is equivalent to 0.100, 0.001. So when you are adding over the one is 0.101. So add the binary value and then convert into one decimal value. Okay. So addition of two fixed point numbers, what will happen now? It causes an overflow. Okay. The next one to be the subtraction of two fixed point numbers. So subtraction, we will be getting that two numbers can be performed by using two's complement representation. So 0.25 from 0.5. So first to find the value of an 0.25 value, we'll be getting the value to be 0.110. Second magnitude 0.010, one's complement to be 1.101 and two's complement to be 1.110. Okay, so the two's complement is given as a minus 0.25. The carry is generated after the addition. Neglect the carry to get the result in this well, because normal subtraction when you are doing over on it, what you'll be getting over on it, 0.5 minus 0.25 will be getting as an 0.25. Okay. Suppose if you are subtracting from 0.25 minus 0.5, you have to get the value of negative representation. So minus 0.25 will be getting over on it. What about the multiplication? So here the sign magnitude components are separated. The magnitude of the numbers are multiplied. Then the sign of the product is determined and applied to the result. So in the fixed point arithmetic, multiplications of two fractions result in a fraction. So that for multiplication with fractions, overflows can never occur. So in additions, we can able to get the value of an overflow value. But in the case of multiplications, So overflow can never occur in the case of an multiplication fixed point arithmetic. The next one to be the floating point representations. So actually here a number floating point number will be represented as an x is represented by x is equivalent to m into r per c. R per E, where M is nothing but an mantissa, that is which requires a sign bit for representing positive numbers and negative numbers, whereas R to be the base or radix and E to be the exponent which require an additional and it may be either positive or negative. For example, 278 can be represented in floating point representations, so which is equivalent to into 1000 divided by 1000, 10 to the power of 3. 0.278 to be the mantissa, 10 to the base or radix, 3 to be the exponent. Similarly, to representation of binary floating point number, x is equivalent to m into 2 to the power of e, in which a fractional part number should be lie in the range of 1 by 2 to 1. So 5 is equivalent to 5 into 8, there is a 0.625 into power 3. So a mantissa and the base or a radix or an exponent. Okay. So negative floating point number representation with respect to the sign of the value. So to represent floating point in multiplications, we will be using of an m1 into r to the power of 1 and m2 into r to the power of 2. So m1 into m2 of r up to the power of 1 plus 2. So, whereas in the case of an addition and subtraction, the exponent of a smaller number is adjusted until the matches exponent of a larger number. Then the matrices are added or subtracted. The resulting representation is rescaled so that its mantissa lies in the range of 0.5 to 1. Okay, so this is a repeated one. What is the comparison of fixed point and floating point arithmetics? When you're saying about a fixed point arithmetic, the fast operations will take place, whereas in the case of a floating point, we'll have a slow operations and relatively economical, whereas in the case of an fixed point, it will be more expensive because of costly hardware in the case of floating point. It have a small dynamic range, whereas in the case of floating point, you have a increased dynamic range. Round of errors occurs only for the additions, whereas in the case of fixed point, whereas in the case of multiplication, round of errors can occur with the additional multiplications. Overflow occur in additions, whereas in the case of overflow does not arise, which is used in small computers, used in large general purpose computers. Okay, so this is about the brief discussion about an fixed point and floating point representations. Whereas in the case of an quantization, so we have to detail about an quantization error which occurs due to the finite word length of registers. So we'll have a common method of quantization or truncation and rounding. So whereas in the case of an truncation, that is the abrupt termination of given numbers having a large string of bits. Or truncation is the process of discarding all bits less than significant in the LSB, that is retained. Suppose if you want to truncate the following binary number from 8 bits to 4 bits. So what we should do it of? So 0.00110011. So remove the last 4 bits. We will get a value 0.0011. Okay. Similarly, 1.01001001 to 4 bits, 1.0100. So when we truncate the number, the signal value is approximated by the highest quantization level. That is not should be greater than the signal. The next one to be the round off. Rounding is the process of binary size of binary number to finite word size of bits. That is, the rounded B bit number is closest to the original unquantized number. So error due to truncation and rounding. So while storing and computing, while storing or computation on numbers, we face registers length problems. Hence, given number is quantized to truncation or rounding off. That is, number of bits in the original number is reduced to register length. So truncation error in sign in magnitude form. So consider 5-bit number which has the value of 0.7815. So which will be truncated to a 4-bit number. So 0.75. There is 5-bit number which has a 1 bits and 4-bit number will have a few bits. Truncation error is nothing but an 0.1100 minus 0.110001. So minus 0.001, which is equivalent to minus 0.03125 to the base one. So original length is L bits, truncate length to be the B bits. So formula truncation error to be 2 to the power of B into 2 to the power of minus L. So this was a repeated question. What is the truncation error for a positive value? 2 to the power of minus B minus 2 to the power of minus L will be 0. Then 0 to 2 to the power of minus B to minus L for the causal number and for an uncausal. So truncation error in 2's complement results in a smaller number, hence remains same as in the case of sign magnitude form. Whereas in the case of a round off error, the error due to rounding, original length to be 5, round off length to be the 4 bits. So now error due to roundings will be given by the formula 2 to the power of minus b to the minus 2 to the power of minus l divided by 2. That b and l are to be the number of bits to the right of binary point after rounding, and ml to be the number of bits to the right of binary point before rounding. So for the positive case, we'll have the formula 2 to the power of minus b to minus 2 to the power of minus l by 2. And for the negative number, we'll have a 0 to the power of minus b to minus 2 to the power of L by 2. For 2's complement, we will have the value of 2 to the power of my B minus A 2 to the power of L by 2. So 2 to the power of minus B to the power of L by 2. So these are all about the introduction about the fixed point, floating point, and the truncation and the rounding process. So next class we will be seeing about an quantization noise. Thank you.